Before I begin, I must say I am not an expert. Most of my information comes from the paper Variational Integrators for Reduced Magnetohydrodynamics by Michael Cross et al. For more information, their paper will be in the description. Anyways, on to the video. For a short introduction, the subject of this video is the creation of a numerical method that takes a simplified model of magnetized plasma and preserves conservation models with a greater accuracy than most methods. The tool we use is called the Variational Integrator that discretizes the action, as in the action of the Lagrangian mechanics, rather than the equations of motion. Variational integrators work in the inverse of traditional methods. In traditional methods, you start with the model, then you define the equation of motion. From here, you discretize the equation of motion. For the variational derivatives, one takes the action, nature selects where. From there, the derivation of such things as Euler-Lagrangian, Hamiltonian, conservation laws. From here, instead of discretizing the differential equations, one discretizes the Lagrangian. From here, varying across a sequence rather than a smooth curve given to you by the discrete Euler-Lagrangian equation. Here, the equation is already an algorithm. No additional methods are needed, though we will use some in the course of our video. In the course of creating this model, we must first define what an RMHD model actually is. But first, we must define an MHD, or Magnetohydrodynamics model. Essentially, it treats plasma as a single conductive fluid coupled with a magnetic field. While it is a massive simplification of billions of charged particles moving about, it is still quite accurate and obviously much less computationally expensive. The reduced Magnetohydrodynamics model further simplifies for a specific, useful physical situation. In plasma with strong magnetic field, like the tokamak, where the field mostly points in one way, call it the toroidal, and everything interesting happens in the plane perpendicular to it. Under those conditions, the fast physics along the strong field direction basically stops mattering, and you're left with an effectively two-dimensional problem, with only four fields remain as useful: the stream function, the vortice, the magnetic potential, and the current density. The equation simplifies to the equation below, with the Poisson brackets being simply the two-dimensional Poisson bracket as seen below. Here we can see that RMHD has Casimir invariant quantities that are conserved, not from traditional physical symmetries, but from the structures of the Lie algebras. There are families with infinitely many subsets. For the purpose of this video, we will focus on magnetic helicity, how tangled the magnetic fields are, and cross helicity, how aligned the flow is with the magnetic field. Now for this paper to work, rather than use the Hamiltonian structure, it uses what is called the Lie Poisson, essentially Hamiltonian's weird cousin. It still conserves energy, but rather than symplectic methods, it uses Lie Poisson. This is because fluid mechanic observables do not naturally describe motion along a phase space, but live in Lie algebra with symmetries within it. So the Poisson operator changes with the state rather than as a constant symplectic structure. Here we come to the snag. Variational integrators need a Lagrangian, an action to discretize, but for RMHD, there is no obvious Euler-Lagrangian. So what does one do? Essentially, we make one up. There is a trick called the formal Lagrangian. Essentially, we take every equation in your system and multiply it by a variable called the auxiliary variable that has no physical meaning. Then you simply add it together. Here, the four variables, psi, mu, chi, and zeta, are all ghost variables that only exist to make the arithmetic work. This helps by adding stationary variables to allow for one to vary the physical variables using Hamilton's principle, leading to a brand new adjoint equation. which brings us to the Euler-Lagrangian, where phi denotes all of the variables, making the auxiliary variables can be found in the function of the original variables. So var phi can be defined as the combination of omega, psi, phi, j, psi, omega, 0, and 0. Now the whole purpose of the creation of the Lagrangian was to apply Noether's theorem. We restrict our attention to conservation laws, which are generated by vertical transformations. That is, a transformation which only affects the field variables, but leaves the base space invariant. From here, we will get into some complex math that I won't get into, but it is found that the symmetries are magnetic helicity, the L-squared norm of psi, cross helicity, and energy. These are ones that we already showed through magnetic helicity and cross helicity, and energy is a simple expansion of the fact that we started with a Hamiltonian. Now, the L-squared norm of psi is something that is new from our formal Lagrangian. Within our current RMHD model, it has a defect. It does not include magnetic reconstruction, when field lines snap and reconnect, which tend to be one of the most important studies in plasma physics. So we will add a small correction, the electron inertia. Real electrons have mass, just a very small one. In the original equation, we treat it as 0, so we will change it by adding their mass. This new term develops in Ohm's law, one that allows reconstruction. Thus, we have our new model, where instead of psi, we grate over psi, which is psi plus d squared subscript e, j, to give the electron canonical momentum, where d subscript e denotes the electron skin depth. That's it. That's the whole modification. From here, small bits of derivation shows that the Hamiltonian stays the same. So does the Casimir invariance and the conservation laws, only expressed in form of psi with a line over it, rather than the original psi. Now before we can put anything in computer, there is some tedious housekeeping needed. Our formal Lagrangian currently has a second derivative, which is highly challenging to discretize directly and even more costly to compute. To do this, we will use what is called symmetrization, essentially integration by parts, but for functionals rather than functions. We do this on the term that produces the Laplace, and then get an equivalent Euler-Lagrangian equation that only depends on the first-order derivative of the fields. Further care can be taken when discretizing the Poisson bracket. It can be seen through integration by parts when assuming appropriate boundary conditions that the cyclic permutations of the functions in the integrad are all identical. Instead of selecting one of these forms, a convex combination can be considered, where alpha, beta, and gamma are all equal to 1/3 to conserve symmetry. From here, we can find the modified Lagrangian. As mentioned earlier, we will discretize the action rather than the equations of motion. For simplicity, we will use the Veslov type finite difference to split into two spaces one at a time, but for extensions, more elaborate approaches are fairly straightforward from here. From here, we can fairly easily find this equation. A large deal of algebra allows us to get to the point of employing the Hamiltonian-Pointarian principle, which states that transforming from a Lagrangian to a Hamiltonian, we should not assume velocity and momentum's relationship, but rather derive it after the fact for treating them independent. Using what we call the Arquois discretization for Poisson brackets, we get the equation below, where the bracket is the averaging of A, which is centered the difference of both x and y, the diagonal interaction, and the diagonal reaction again, but rotated relative to the other. Using these principles, a lot of mathematics, we gained these massive equations. If you wish to see the derivation out, I would recommend reading the paper below. Using the same methodology, we can find earlier conservation laws. We have total energy, magnetic helicity, L squared norm of psi, and cross helicity. Now we have an implicit form tangled in nonlinearity. To solve this, we use Newton's method, linearize the residual. Solve the resulting linear system, update your guess, repeat until the residual is essentially zero. That linear system at each Newton step gets handed off to GMRES, an iterative Krylov subspace solver. And to make GMRES converge fast, they build a custom physics-informed preconditioner, following earlier work by Chachon and collaborators, that exploits the specific structure of the voricity and Ohm's law equations. The elliptical bits, inverting the Laplace to get the variables, get handled by whatever general-purpose elliptic solver you have on hand. They use PETSC. If your domain happens to be doubly periodic, there's an even cleaner trick available, since the periodic boundary condition means the discretized Laplace is exactly diagonalized by a fast Fourier transform, so you can invert it directly and exactly in Fourier space. No iteration is required. I mimic this in a Python by setting up a file to create the initial conditions, operators of spectral solver in Araka's method, an integrator file to run it through the actual equations derived earlier. Here, I make sure my model matches the paper through the Orsang-Tang vortex. Then I check a current sheet, then a current sheet with electron inertia. Here, the models match that of the paper and matches within machine precision of the analytical solution. Now that we have a working model, we can do something cool with it. Here is a kinetic affine turbulence movie.